To determine if two particles, such as a photon and an electron, are entangled, we examine their quantum state. The key concept is factorization, which relates to how the quantum state of the system can be expressed. Quantum state of two particles. In general, the state of a two-particle system is represented by a joint wave function or state vector in the combined Hilbert space, where H1 and H2 are the Hilbert spaces of the individual particles. Factorization and entanglement. If the state ket psi can be factorized into a product of the individual states of the photon and electron, i.e., ket psi equals ket phi sub 1, tensor, ket chi sub 2, where ket phi sub 1 is the state of the photon and ket chi sub 2 is the state of the electron, then the two particles are not entangled. If the state cannot be written in this factorized form and instead requires a more general expression, such as where C sub ij are coefficients that cannot be separated into products of terms for each particle, then the particles are entangled. To verify entanglement, simply multiplying the states ket phi sub 1 and ket chi sub 2 would assume separability. The goal is to determine whether such a factorization is possible. The absence of factorization, and the presence of non-local correlations in the state coefficients, is what signifies entanglement. Let's use a simple arithmetic analogy to explain the concept of coefficients that cannot be separated into products of terms for each particle. Analogy with arithmetic. Factorizable state, not entangled. Suppose you have a mathematical expression where A sub I and B sub j are numbers corresponding to particle 1 and particle 2, respectively. For example, C sub ij equals 2 times 3 is equal to 6. This is a product of terms, so the expression is separable, not entangled. In quantum terms, this corresponds to a factorized state like ket psi equals ket phi sub 1, tensor, ket chi sub 2. Non-factorizable state, entangled. Now consider an expression where C sub ij cannot be written as a simple product of terms for each particle. For example, C sub ij equals 2 plus 3 is equal to 5. This sum involves contributions that cannot be separated into independent terms for each particle. In quantum terms, this corresponds to an entangled state, which might look like quantum state example. Separable state, not entangled. The coefficients of the joint state are products of individual states. Entangled state. The coefficients of this state, e.g., 1 over square root of 2, involve a correlation between the two particles that cannot be separated into terms for each particle. Takeaway. The inability to express C sub I, j, as a product, e.g., C sub ij equals A sub I, B sub j, indicates entanglement. The presence of sums or more complex correlations, analogous to 2 plus 3 instead of 2 times 3, highlights this non-factorizable nature. Let's construct a separable, not entangled, quantum state for an electron and a photon with simple numerical coefficients. Scenario. The electron state can be described by two possible states, ket E1 and ket E2. The photon state can be described by two possible states, ket P1 and ket P2. The joint state is separable, meaning it is a product of the electron state and the photon state. Example of a separable joint state. Let's say the electron state is ket phi electron equals A1 times ket E1 plus A2 times ket E2, where A1 equals 1 over square root of 3 and A2 equals square root of 2 over 3. The photon state is ket chi photon equals B1 times ket P1 plus B2 times ket P2, where B1 equals 1 over 2 and B2 equals square root of 3 over 2. The joint state is given by the product. Ket psi equals ket phi electron, tensor, ket chi photon. Photon. Expanded joint state. Substituting the individual states. Expand the product. Coefficients. The coefficients of the joint state are products of the individual coefficients. Final joint state. Key observation. The coefficients of the joint state are products of the electrons and photons' coefficients, so this state is not entangled.